Have you ever heard about the mysterious volcanic tsunami that occurred in 1650? During the late summer of that year, strange occurrences began to unfold off the island of Santorini. Eyewitnesses reported that the sea transformed, changing color and appearing as if it was boiling. Just 7 kilometers northeast of the island, an underwater volcano was stirring, ready to unleash its fiery wrath. The volcano erupted, spewing glowing rocks across the sea. Fire and lightning danced across the sky. A thick, ominous blanket of smoke shrouded the heavens, casting a foreboding darkness upon the island. And then, in a terrifying spectacle, the sea withdrew. As the water receded, a monstrous wave, 20 meters high, rose from the sea. A crash echoed, so loud it was heard more than 100 kilometers away. The wave, partnered with clouds of deadly gas, wreaked havoc, claiming several lives in its destructive path. This catastrophic event became known as the Columbus eruption. For more than 370 years, geologists have pondered over what could have triggered such a disaster. Theories were proposed, yet none could provide a definitive answer. But today, we stand on the brink of a breakthrough. Researchers at the Helmholtz Centre for Ocean Research Kiel, or GEOMAR, may have unlocked the secret behind the Columbus eruption. Their findings, published in the journal Nature Communications, hint at a plausible cause of the disaster. The researchers used seismic imaging technology to investigate the underwater volcano, creating a three-dimensional reconstruction of the Kolumbo crater. The images revealed a massive eruption and signs of a landslide, pointing to a dual cause for the tsunami. Could it be that both a landslide and a volcanic eruption are responsible for the devastating tsunami of 1650? As we delve deeper into the investigation, we find ourselves closer to unraveling the mystery. For centuries, the trigger of this disaster remained a mystery, but not anymore. Known as the Columbus eruption, this event has puzzled geologists for a long time. It was a spectacle that unfolded in the late summer of 1650, off the island of Santorini. The waters inexplicably changed color, began to boil, and then the unexpected happened. An underwater volcano situated about 7 kilometers northeast of the island erupted with such force that it spewed out glowing rocks into the sky. The eruption was so intense that it was accompanied by fire, lightning, and a thick blanket of smoke that obscured the heavens. This was no ordinary volcanic eruption. As the water receded, a colossal wave, 20 meters high, rose from the sea. The impact was felt more than 100 kilometers away. The wave, coupled with clouds of poisonous gas, claimed several lives, leaving a lasting imprint on the pages of history. This event, christened as the Columbus eruption, has since intrigued and baffled geologists. The question that has long stood unanswered is, what triggered this disastrous event? Researchers at the Helmholtz Centre for Ocean Research Kiel, or GEOMAR, embarked on an investigation to unravel this mystery. They used seismic imaging technology to create a three-dimensional reconstruction of the underwater volcano referred to as the Kolumbo crater. The images revealed an enormous eruption, and the crater, a gaping void, 2.5 kilometers wide and 500 meters deep. One side of the volcanic crater was heavily deformed, a potential indication of a landslide. So, was it a mighty landslide or a volcanic eruption that set off the powerful tsunami? The researchers pondered upon this question. Through a combination of three-dimensional images and computer simulations, they arrived at a conclusion. It was a combination of both a landslide and an eruption that triggered the giant wave. The key to the mystery may lie at the very bottom of the ocean. Enter the researchers at the Helmholtz Centre for Ocean Research Kiel. Armed with a thirst for truth and the tools of modern science, they set out to unravel the mystery that has puzzled geologists for centuries: the Columbus eruption. To delve into the depths of this enigma, they employed seismic imaging technology, a method that uses sound waves to create a detailed, three-dimensional image of the Earth's interior. It's like taking an X-ray of the planet, revealing the unseen structures hidden beneath the surface. The target of their investigation? The Kolumbo crater, an underwater volcano located northeast of Santorini. What they discovered was nothing short of astonishing. The Kolumbo crater was a massive geological formation stretching 2.5 kilometers wide and diving half a kilometer deep into the ocean floor. But perhaps the most intriguing part was the heavy deformation on one side of the crater, a potential sign of a landslide. The evidence pointed to a landslide, but was it the only cause? The researchers had to consider another possibility, a volcanic eruption. To discern between these two scenarios, they turned to a combination of their 3D seismic images and advanced computer simulations. The result? A stunning revelation. The seismic images and simulations provided the researchers with a clear chronology of the events. Comparing these findings with historical accounts of the water receding and the thunderous crash that followed, they concluded that the giant wave was triggered by not just one but two catastrophic events: a landslide and a volcanic eruption. To paint a clearer picture, imagine the steep slopes of the Kolumbo crater made unstable by weeks of continuous volcanic activity. As one of the flanks began to slide, it was akin to popping the cork off a champagne bottle. The sudden drop in pressure caused the gas within the magma system to expand, culminating in a massive explosion. The evidence pointed to a landslide, but was it the only cause? The answer to that would be revealed in the next chapter of our investigation. The question was, landslide or eruption? The answer is both. The researchers from GEOMAR stood at the intersection of geology and history, piecing together the puzzle of the Columbus eruption. Their conclusion? Both a landslide and an eruption were responsible for the cataclysmic tsunami of 1650. The analogy they used to explain this dual trigger mechanism is both vivid and enlightening. Picture a bottle of champagne. It's been shaken up, the pressure inside building, the liquid fizzing with potential energy. The cork represents the flank of the volcano holding back the force within. Now imagine the cork is suddenly removed. The pressure inside drops instantaneously, the gas expands, and with a celebratory pop, the champagne is released in an effervescent explosion. This is essentially what happened at the Kolumbo crater, but on a much more catastrophic scale. The volcano's flank, unstable due to the steep slopes of pumice, began to slide. This landslide, much like removing the cork of a champagne bottle, resulted in a sudden drop in pressure within the magma system. The gas within the magma expanded rapidly, resulting in a massive explosion, an eruption that spewed lava and sent shockwaves through the surrounding water, triggering the devastating tsunami. The researchers had to meticulously piece together the evidence, comparing their 3D images and computer simulations with historical accounts of when the water receded and when the colossal bang was heard. Their conclusion that both a landslide and an eruption were responsible for the tsunami was a groundbreaking revelation. The research findings didn't just solve a centuries-old mystery, but also provided valuable insights into the behavior of underwater volcanoes. These discoveries could potentially revolutionize how we monitor volcanic activity beneath the sea surface, and could lead to the development of early warning systems for future eruptions. The Columbus eruption, the landslide, the eruption, and the resulting tsunami, a sequence of disastrous events that unfolded in 1650, had finally been fully understood. A mystery that had lasted for over 370 years was finally solved. But the revelations didn't end there. The findings from the Columbus eruption not only solved a mystery that had puzzled scientists for centuries, but also opened up a new avenue for understanding and predicting similar disasters in the future. The seismic imaging technology and 3D reconstructions used in this investigation allowed the researchers to visualize the eruption in a way that was never before possible. This methodology provided the clarity needed to discern the dual cause of the catastrophic event, the landslide and the eruption. This dual cause theory brings us to the Hunga Tonga Hunga Ha'apai volcanic eruption back in 2022. The researchers at GEOMAR believe that a similar scenario might have unfolded in this case. The sheer magnitude of the Hunga Tonga Hunga Ha'apai eruption, which caused extensive damage to the sea floor and the ozone layer, suggests that it too could have been triggered by both a landslide and an eruption. If this theory holds true, it could revolutionize our understanding of underwater volcanic activity and the way we predict and prepare for such events. The ability to identify the signs of an impending landslide or eruption could provide the crucial minutes or hours needed to evacuate and secure areas at risk. Moreover, these findings could lead to the development of new methods for monitoring underwater volcanic activity. By using seismic imaging technology and computer simulations, we could potentially create a comprehensive system that can warn us of future eruptions in good time. This would be an immense step forward in our efforts to safeguard lives and property from the devastating impact of volcanic tsunamis. The research conducted on the Columbus eruption serves as a stark reminder of the powerful and often unpredictable forces that shape our planet. It underscores the importance of continuous research and innovation in our quest to understand and coexist with these forces. The story of the Columbus eruption, once a mystery, now serves as a beacon, illuminating our understanding of underwater volcanic eruptions and tsunamis. A mystery solved and a step forward in understanding our planet's powerful forces.